All right, welcome you to this lesson. And in this lesson, we are going to cover carbonyl compounds. Basically, we're going to look at the introduction, we're going to look at the nomenclature and the preparation of these carbonyl compounds. So, when we say carbonyl compounds, okay, they are organic compounds with a carbonyl functional group. The carbonyl functional group is indicated by C, double bond O, then, so this is our carbonyl group, right? Then another thing we need to note that carbonyl compounds can be aldehydes and ketones, but they have got the general formula, which is CnH2nO. What you need to know about organic compounds that are in the same homologous series, they have got the same general formula. And in this case, where you find aldehydes and ketones in the same class, the carbonyl compounds, then they take on the same general formula. Now, the difference between the aldehydes and ketones is that aldehydes possess a hydrogen atom attached to the carbonyl carbon. Okay, they possess a hydrogen atom attached to the carbonyl carbon. For example, actually the general representation would be R, C, double bond, O, then H. They possess a hydrogen attached to the carbonyl carbon. While ketones have two alkyl groups attached to the carbonyl carbon. So we have the carbonyl carbon, right? But we're saying that we have two alkyl groups attached. So these are ketones, these are aldehydes. So we are going to look at the details of these compounds, okay? And this one will give us a clear picture of what carbonyl compounds are. All right, now looking at this, the ones which are the saturated aliphatic, this general formula is for the saturated aliphatic carbonyl compounds, but for those ones that are cyclic, the cyclic ketones, basically the cyclic ketones have got the formula CnH2n minus 2. Then these are cyclic ketones. Now, I told you that the difference in the structure of ketones and aldehydes, because they are different in structures, so this difference in structures affect the properties of these compounds in basically two ways, okay? Whereby aldehydes are quite easily oxidized, while ketones are oxidized only with a lot of difficulty. Two, that the aldehydes are usually more reactive than ketones towards nucleophilic addition. That is as a result of the difference in their structures. Let's rush quickly to nomenclature of these organic compounds, the ketones and the aldehydes. Nomenclature. Our nomenclature we follow the IUPAC, okay? We follow the IUPAC system of naming these carbonyl compounds, right? And nomenclature of aliphatic aldehydes considers dropping the ending E we shall realize that instead of ending E, we shall be having al. Shall be having al. Al. So, in other words, where you were supposed to have ethane instead of something like ethane, for us we say ethanol for this case, okay? So the main carbon chain is named as usual, and the carbonyl carbon is considered as the carbon number 1. Where you have the carbonyl carbon, we consider it as carbon number 1. For example, if you have this formula HCHO, we call this methanol. Methanol. If we have CH3, CHO, we call this one ethanol. We call it ethanol. If you have CH3, CH2, CHO, we call this one propanol. Propanol. So instead of propane, that ending E for alkanes is replaced with al. Okay, we have butanol. Then I've also had this CHO. This one we call it benzaldehyde. This one is called benzaldehyde. So if you have a case like for this compound here, like CH2, CHO, we call this one phenylethanol. Phenylethanol. All right. Then if you have a case like CH3, CH, then CH3 here, then CHO. You see, we have a methyl group on the second carbon, so we say 2 methyl, and then the bond chain is for propane, so 2 methyl propanol, right? Then in a case where you have something like this compound, this one we shall name it as, you see, 1, 2, 3, 4, because you see that the carbonyl carbon is counted as carbon number 1. So 1, 2, 3, 4. We shall have 4 methyl benzaldehyde. 4 methyl benzaldehyde. The same applies to when you have a nitro group attached. When you have a nitro group attached, see, this is 4 nitro benzaldehyde. 4 nitro benzaldehyde. This is read as 4 nitro benzaldehyde. Then a case where you have like benzene ring, then here you have CHO, and then here you have OH. We call this, this is carbon 1, carbon 2, so we call it 2-hydroxybenzaldehyde. 2-hydroxybenzaldehyde. So that is basically for aldehydes. Then for ketones, for the case of ketones, we derive the names by taking the stem of the name of the corresponding alkane, and we replace the ending E of alkanes, we replace it with the on. We replace it with the on. We replace the ending E with the on. Right? So we need to know that the position of the carbonyl group is indicated by a number. Right? The position of the carbonyl group is indicated by a number. Okay? So we're going to find that the carbonyl carbon is being given the lowest number. For example, if we write like CH3, CO, CH3, this one I'm going to call it propanol. Propanol. If you have something like CH3, CO, CH2, CH2, CH3, 1, 2, 3, 4, 5. But the lowest number of carbonyl is 2. So this is pentane 2 on, pentane 2 on, pentane 2 on. But if you have like CH3, CH2CO, CH2, CH3, this is called pentane 3. Pentane 3 on, right? Then in a case where you have this is cyclohexanone. Cyclohexanone. But it's supposed to be, if this was not there, it was supposed to be cyclohexane. Now by putting a carbonyl group, it becomes cyclohexanone. Then if you have like this, this is cyclobutanone, 1, 2, 3, 4 carbons. So this is cyclobutanone. We've gotten many others. We've gotten very many others. If you have like this, this is also a common compound. This is phenylethanone. We call it phenylethanone. Phenylethanone. Then in case where you have something like I have this compound. This is diphenylmethanone. Diphenylmethanone. And etc. etc. So though that is how we can name a few of them. Right? That is how we can name a few of those carbonyl compounds. Then from there, we can go to the physical properties. Physical properties. Physical properties, of course, the first one would be the physical state. Now, when you talk about the physical properties, you're looking at the XP, the appearance and those physical properties of solubility, boiling points. You see, something related to that. Now, when we talk about the physical properties of carbonyl compounds, all right, so we may simply say that aliphatic aldehydes and ketones of lower molecular mass are colorless liquids, okay? And those with high molecular mass are solids. That is basically what we can talk about it. The ones of low molecular mass are colorless liquids at around 20 degrees Celsius, but those ones with high molecular mass, they are solids. Then property number 2 would be solubility. Solubility. Those ones, the liquid aldehydes and ketones of low molecular mass, they are very, very soluble in water. Very soluble in water. For example, methanol, ethanol, and propanol. Methanol, ethanol, and propanol are all miscible with water. Methanol, the ones of low molecular mass. Methanol, ethanol, and propanol are all miscible, are very soluble in water. Simply because their solubility is connected to the intermolecular hydrogen bonds they form with the water molecules. The solubility is attributed to the hydrogen bonding. So we have partially positive, partially negative, partially positive, partially negative. We have H, partially positive. So we are saying that the ones which are highly, which have low molecular mass are highly soluble, but those ones which have more than 5 carbons and the ones which are aromatic, they are insoluble in water. So the ones with the greater than 5 carbons and aromatic ones, aromatic carbonyl compounds, all these ones are insoluble. So that is the biggest point to note. All right. Of course, you say that solubility decreases with an increase in the size of the molecule, because the increase in the molecular size distorts the formation of hydrogen bonds with the water. So let's talk about another factor of boiling points. That is also another physical property. When you talk about boiling points, now here I want us to examine the occurrence of these carbonyl compounds. All right. Now, the carbonyl group is polar. The carbonyl group is polar. We are having oxygen and carbon on that carbonyl group, but because they have gotten different electronegativity values, all right, that difference in electronegativities makes them become polar. In other words, the polar carbonyl group makes the aldehydes and the ketones polar compounds, and hence they have higher boiling points than the non-polar compounds of comparable molecular weight. We said that their polar nature makes them have a higher boiling point. For example, we can realize that propanol, okay, has a higher boiling point than butane. Propanol has got a boiling point of 56 degrees Celsius, while butane has got a boiling point of negative 0.5 degrees Celsius. Yet, both have the same molecular weight. You should compute their molecular weight. Propanol is CH3, COCH3. Butane is CH3, CH2 times 2, then CH3. Otherwise, you'd have said CH2, CH2. But when you compute their molecular weight, this one is carbon 12 plus hydrogen is 3. So plus carbon 12 plus 16 plus 12 plus 3. So this is 24, 36, 52, 55, 58. So propanol has molecular mass of 58. The same applies here. Carbon is 1, 2, 3, 4. So this is 48 plus 3, 4, that is 7, then 10, which gives 58. But we want to see, why is it they have the same molecular mass, but why is it that propanol has got a higher boiling point compared to butane? This question can appear in an exam. They can say, explain the following observation. Propanol boils at 56 degrees Celsius, while butane boils at negative 0.5 degrees Celsius, yet the two compounds have got the same molecular weight. So we want to see what brings about that aspect. All right? So when you draw these ones, you'll see that you have CH3, CO, then CH3, partially positive, partially negative. Then this one is just open like that. CH3, CH2 times CH3. When you look at this, the oxygen atom in propanol is, the oxygen atom in propanol is more electronegative than carbon. That is the first statement you need to first give me. Okay, the oxygen in propanol is more electronegative than the carbon to which it is bonded. Therefore, being more electronegative, it means that oxygen pulls the bonding electrons towards itself. And as it pulls electrons towards itself, the moment electrons are gained by an atom, it becomes partially negative, leaving the carbon partially positive because electrons are being extracted from carbon to the oxygen. So the oxygen becomes partially negative and the carbon acquires a partial positive charge, which makes the carbon-oxygen bond polar. This one being partially positive, this one being partially negative, having different electronegativity values, or that difference in electronegativities makes the carbon-oxygen bond polar, and then therefore the whole molecule ends up becoming polar. What does it mean? Propanol molecules, therefore, are held together by stronger forces of attraction, or what we may call the permanent dipole-dipole moment, or the permanent dipole-dipole van der Waals forces of attraction that require enough energy to break. However, in butane, the molecules are nonpolar. When the molecules are nonpolar, it means that they require lower amount of energy to break. Why? Being nonpolar, they have got weaker forces of attraction, which we call the temporary dipole-dipole van der Waals forces of attraction, right? That are easily broken. So one can explain it along that lane. First telling me that the oxygen, let me summarize it for you. The oxygen atom in propanol right? The oxygen atom is in propanol is more electronegative than the carbon atom. Okay, you can say that the carbon atom to which it is bonded. What does it mean? It therefore pulls the bonding electrons right? Put the bonding electrons more towards itself. All right. What is itself? Gaining a partial negative charge. All right. While the carbon atom gains a partial positive charge. So basically that is what I wanted to talk about. Then the other things I can repeat them and maybe you write them. So it means that the carbon oxygen bond becomes polar, making the whole molecule polar. Meaning that propanol molecules, okay, are held together by stronger intermolecular forces of attraction that we call the permanent dipole-dipole van der Waals forces of attraction, which are hard to break or which require a lot of energy to be broken. But butane molecules are nonpolar, hence have weaker forces of attraction, or what we call the temporary dipole-dipole van der Waals forces of attraction that require low amount of energy to break. Right? So we need to know that. But another thing you need to know that carbonyl compounds have lower boiling points compared to alcohols or carboxylic acid of comparable molecular mass. For example, they can ask you, we've said that with alkanes, for example, with propanol and butane, we've seen that propanol has got a higher boiling point because of that difference in electronegativity that makes the bond holding its molecules together very strong. But they can bring you a question also whereby ethanol boils at 21 degrees Celsius, while ethanol boils at 78 degrees Celsius, yet they have almost equal molecular mass. If they have almost equal molecular mass, why is it that the other boils at a lower boiling point than ethanol? Now, what we need to know that ethanol cannot form the intermolecular hydrogen bonds between its molecules. Its molecules only interact through weak van der Waals forces of attraction that require low amount of energy to break. But for ethanol, the oxygen atom is more electronegative than the hydrogen atom to which it is bonded. So the oxygen gains partial negative charge and the hydrogen gains a partial positive charge, making the oxygen hydrogen bond polar, and ethanol molecules interact through intermolecular hydrogen bonds that require high amount of energy to be broken. So we are looking at this ethanol taking on hydrogen bonding, right? At the same time, we're talking about hydrogen bonding, and then that difference in electronegativity between the oxygen and the hydrogen, right? So, which is not the case in ethanol. Ethanol does not form hydrogen or intermolecular hydrogen bonds between its molecules. So that mere failure to form intermolecular hydrogen bonds between its molecules, it makes its molecules interact through weak van der Waals forces of attraction that require low amount of energy to be broken. So that is what we need to know. We talk about it not forming the intermolecular hydrogen bonds, its molecules being held together by weak van der Waals forces of attraction, which are easy to be broken. But ethanol, for the case of ethanol, we've said that the oxygen, not ethanol, the oxygen and the hydrogen have gotten different electronegativities, with oxygen being more electronegative than hydrogen. So it means that the oxygen being more electronegative should be pulling bonding electrons from hydrogen to itself, and thus it will acquire a partial negative charge, while the hydrogen will acquire a partial positive charge, making the bond also polar. When the bond is polar, then in addition to ethanol molecules interacting through intermolecular hydrogen bond, then the whole molecule requires a lot of energy for it to be broken. So that is all about this introduction and physical properties. But basically, we need to know how to obtain these substances, the common term called synthesis, how to synthesize these compounds. Okay. Laboratory preparation. We shall look at the isomerism after laboratory preparation. So let's see how we can synthesize these compounds from the lab. Laboratory preparation. First method, we can get them from oxidation of alcohols. You need to know that when primary alcohols are oxidized using strong oxidizing agents, right? When a primary alcohol is oxidized, we form what we call an aldehyde. So aldehydes are prepared by controlled oxidation of primary alcohols using acidified potassium dichromate 6 solution or acidified potassium permanganate solution. Right, so we shall just say CH3, CH2, OH, we shall say acidified potassium dichromate, aqueous, but it must be acidified. Then we warm, don't heat, we warm. When we warm this ethanol, we shall form ethanol. Mere being being a primary alcohol, it gets oxidized to an aldehyde. So you need to know that primary alcohols go to aldehydes. This reagent, one can as well write it as Cr2O72 minus H plus. Still, that is acidified potassium dichromate 6. All right. If you have an aromatic one, if we also oxidize this, I can use now potassium permanganate, aqueous, of course, then warm, we shall form benzaldehyde. However, here we've said one can write manganate, a manganate ion with an acid. Here, one can as well write down a ionic equation. One can say 3 molecules of ethanol plus a dichromate plus, of course, ethanol is a liquid, then plus an acid. The moment you warm that, we shall get ethanols. Then this one being a strong oxidizing agent, it is reduced to chromium 3. Should have a 2 here. Then water. So that is how one can as well use that equation. Now, you need to note that primary alcohols can undergo secondary oxidation to carboxylic acid, but our interest is basically carbonyl compounds. Now, the aldehyde can be distilled from the mixture as it is formed, but I want to look at further oxidation, because further oxidation of this would give you ethanoic acid, but don't go that far. So that is the first method of preparing these aldehydes. Another method still, we can as well use acidified chromium 6 oxide. But before I go to acidified chromium 6 oxide, since in the first case, we have oxidized the primary alcohol, I'm to take you back, You oxidize the primary alcohol to form an aldehyde. But you said that when the reaction is not controlled, it can go ahead to form a carboxylic acid by going under further oxidation. So to avoid that further oxidation, it's better to use dichromate 6 solution than manganate 7 solution, since the dichromate ions are milder in oxidizing action, or they are not as too much oxidizing as the permanganate. So that's why you're saying that the best alternative is to use the dichromate, okay? Avoid further oxidations. But still, other oxidizing agents can work. For example, we've said that acidified chromium 6 oxide, acidified chromium 6 oxide can as well be used, or one can as well also use acidified manganese 4 oxide. Acidified manganese 4 oxide. For example, if you have ethanol, can acidify, rather you can oxidize using chromium 6 oxide acidified, which is CrO3 with an acid. Here we heat, and still we go to our ethanol. Alternatively, you can use acidified manganese 4 oxide. Still, you go to ethanol. So when you use acidified manganese 4 oxide, and heat, still you find yourself that way. That is how we get aldehydes from primary alcohols. Then to get ketones, we oxidize secondary alcohols. So ketones, for the case of ketones, we get them by oxidizing secondary alcohols. So in other words, before you do carbonyl compounds, you need to have ideas about alkyl halides, how we can use alkyl halides to get alcohols, and how we can use alcohols to get either an aldehyde or a ketone, depending on what the questionnaire wants. So that one, we shall look at a detailed jazz. We shall have a detailed jazz about synthesis. We shall get examples that we shall synthesize at the end. We shall have general examples. So ketones can be formed by oxidizing the secondary alcohols, basically using acidified potassium dichromate 6 solution, or acidified potassium manganate 7 solution, or acidified chromium 6 oxide, or acidified manganese 4 oxide. So all those, I'm going to summarize them here. I've said that if we have a secondary alcohol, for example, CH3, CH, OH, CH3, that is propan2-ol. So if we oxidize it using potassium dichromate, and we heat this time, we shall form propanone, CH3, C double bond, or CH3, that is propanone. Or one also can form that by using potassium permanganate. And we heat. Or we've said that one can use as well, one can use the chromium 6 oxide, CrO3, H plus, then we heat. Or one can use manganese 4 oxide and you heat, MnO2, then we heat. So still we shall form our we shall form our compounds, or we shall form our respective ketones. Now, also you can oxidize. Oxidation can also be done by the hydrogenation of alcohols when passed over copper-2 catalyst. And when you use copper-2 catalyst, we have to heat about 300 degrees Celsius. So in other words, what I'm trying to say is that as well, you can have ethanol. You oxidize it using copper catalyst at 300 degrees Celsius. Still, this one will form ethanol. You can have propanol. No. You can have propan-2-ol. Use the same reagents. You use copper catalyst at 300 degrees Celsius. Still, it will take you to propanol, CH3COCH3. All right. On an industrial scale, by oxidizing methanol, we can get ethanol. No. By oxidizing, methanol, we can get methanol. And by oxidizing ethanol, still we can get ethanol. That is on an industrial scale. But there, we use oxygen and silver catalyst. So, industrially, but still we are continuing with the laboratory preparation, only that I've just brought it in. If you have methanol vapor, and you oxidize it using oxygen and silver catalysts at 500 degrees Celsius, you form methanol. If you have ethanol, CH3, CH2OH, and you oxidize it using silver catalyst at 500 degrees Celsius, we shall form ethanol, CH3CHO. So all these methods can work. All those methods can work. Okay, so now from there, let's look at another method that we can use to obtain carbonyl compounds. We can oxidize methyl benzene. The second method is oxidation of methyl benzene. Oxidation of methyl benzene. In my previous video, I recorded everything about methyl benzene. Now, this methyl benzene, or what you call toluene, is basically used to prepare benzene carbaldehyde or benzaldehyde, okay? Nothing else. So what happens is that the methyl group on the benzene is oxidized using, you can use chromium 6 dichloride dioxide, because we say that you can use chromium 6 dichloride dioxide, write it like that, no condition down. You get your benzene carbaldehyde or your benzaldehyde, CHO. This is benzaldehyde. But this reagent, because you may need to mention the name in case they say without using equations. So this is, we shall do anyway, we shall do examples about synthesis after doing the preparation. So this is, you can read it as chromium 6 dichloride dioxide, or one can call it chromyl. One can call it chromyl chloride. This is very, very, very interesting. Now, also, you can use acidified manganese 4 oxide or acidified chromium 6 oxide, but those ones would require heating. So still here, to go to this, you'd use manganese 4 oxide, which is acidified, and you heat. Alternatively, you can as well go there by using chromium 6 oxide, acidified, and then you heat. As simple as that. As simple as that. So oxidation of methyl benzene, or what we call toluene, can make you have the final answer. Yes, then from here, we can as well get them from another method, because we have to discuss almost all the methods and tonight. So let me see. When we're doing alcohols, still, I forgot this, but add it. If you have like phenyl, cyclohexanol, if you oxidize it, chromium 6 oxide, acidified, and then you heat, you get your cyclohexanone, something like that. Right. So another method of preparing these compounds would be through we can get them from hydrolysis of Germino dihalides. Hydrolysis of Germino dihalides. When we say Germino dihalides, you need to know the meaning of the word Germino. So when we say Germino, I'm trying to think about what my viewers are thinking. When we say Germino dihalides, it means that two atoms or functional groups are attached to the same atom, because the word Germino comes from the Latin gemini, Latin gemini, which means twins. So when we say Germino dihalides, it means that I'm having halide or halogen atoms. I'm having the halogen atoms, okay, attached to one carbon. So Germino dihalides are hydrolyzed with aqueous sodium hydroxide to form ketones or aldehydes, depending on the position of the halogen atoms. For example, if the halogen atom, or if my Germino dihalide is this CH3, CH2, then C, Cl, Cl, then H. That is a Germino dihalide. If I treat it with aqueous sodium hydroxide and I heat, went from CH3, CH2, CH, then O. Okay, that is what I do form. Then O, that is what I do form. But imagine a scenario that we have CH3, C, Cl, Cl here again, then CH2, CH3, and you're having aqueous sodium hydroxide, and then you heat. Now you have CH3, where these dihalides, where you have two halogen atoms attached to one carbon, is where we have our functional group CO, CH2, CH3. That is how we have it. Now, this method is not commonly used for aliphatic compounds because of the difficulty of obtaining dichloro compounds. Obtaining these dichloro compounds when it is a synthesis from a certain stage, it is very hard, all right? However, when we prepare benzaldehyde, we can form it using the method, because dichloro compound is easily obtained by free radical chlorination of methyl benzene. With benzaldehyde, it can be easily formed, because if you have methyl benzene, by chlorination under UV light, the moment you heat, you're going to get because it will undergo free radical mechanism, and you have CH-Cl2, which is the dichloro compound. Now here, hydrolysis alone can be used to effect this hydrolysis. So we shall just say water at 100 degrees Celsius, and we form our benzaldehyde. So in other words, here with methyl benzene, you can take to a dichlorphenylmethane, then you add water, or you hydrolyze with water at 100 degrees Celsius, which is the boiling point of water. So in other words, you boil with water, then you form your benzene carbaldehyde or benzaldehyde. So that is hydrolysis of Germino dihalide. So where you have two halogen atoms attached to one carbon. So let's look at another preparative method. Another method we can use is decarboxylation. If I go to decarboxylation, we can get it from Grignard's reagent. From Grignard's reagent. So if we had to prepare this from Grignard's reagent, all right, we need to know what Grignard's reagent do in this particular case. So with Grignard's reagent, we prepare ketones. And these ketones are prepared when a Grignard reagent is added to an alkyl or an allyl nitrile allyl nitride and the product hydrolyzed with the dilute acid. We cannot use a cyanide in this case. So in other words, I'm having Grignard reagent R MgBr. One, I can use RCN with dry ether at 0 degrees Celsius. Then two, I can follow this with hydrolysis, presence of an acid. So this one forms RC or R prime, which is a carbonyl compound, and this is a ketone. This is a ketone. E.g., you can have a cyanide. So to be factual, we shall have the first reagent as CH3 maybe, CH2, MgBr. This is the Grignard's reagent. And we shall treat it with the dry ether at 0 degrees Celsius. Then two, we shall add water and a dilute hydrochloric acid. So this one will lead to the formation of shall form CO CH2CH3. All right, so that's what you have. Even if you have CH3, CH2, CN, use same reagents here. Rewrite all of them here. The way I've written them here, bring them again here. So there, we shall form CH3, CH2. Then I bring in my CO, CH3. So that is what we call that is how the Grignard reagent works. After the Grignard reagent, let's see how we get these compounds from a decarboxylation. Decarboxylation. Decarboxylation of calcium salts decarboxylation of calcium salts of carboxylic acids. So here we have a calcium salt of carboxylic acid. I'm sorry for this. Let me write my compound word, CH3, COO, 2Ca. So this is my calcium salt of a carboxylic acid. You see, this is a carboxylic acid, but we are having calcium. So this means that it is calcium salt. Now, when you have this, we have to add more And this one will give us, if we dry distill, we shall dry distill at 400 degrees Celsius. And here you get 2 molecules of propanol plus, then this one will form calcium carbonate. That is calcium carbonate. Right. Then still we can note that if we have calcium salt of carboxylic acid, CH3, 2, then Ca. The moment you heat this to decompose to form CH3, COCH3 will come from here because you have 2 CH3s, then O, then plus calcium carbonate. So still that one works. And one may wonder how we prepare these carboxylic, how we prepare these salts of carboxylic acid, right? For example, if I have propanoic acid, so when we add calcium carbonate in this, we shall form CH3 and then when heated, we shall form CH3, CO, CH2, CH2, CH3. That's what you would expect. Then still when you do from here, you can branch from here and you add, branch from here, you add HCOO, 2, then we dry distill at 400 degrees Celsius. Still, you're going to form the same product, CH3, CH2, CH2, CHO. So that is what we do. Now we've said that calcium salts of carboxylic acids, when heated, they compose to form ketones. Calcium salts of carboxylic acids, when heated, they compose to form ketones. And of course, it manifests itself from here. The salt decomposed to form a ketone. All right. So actually, very many processes can give you the answers. Even when you consider salts of other substances like calcium, magnesium, they will give you propanol and the carbonate of an element. So you can use that one of calcium, how it decomposes to get the rest of the answers. Then we have what we call this method of Friedel-Crafts acylation. Can you get this by Friedel-Crafts? Acylation. It's very easy because this one we just form aromatic ketones by reacting benzene with acyl chloride in presence of aluminum chloride as a catalyst. So Friedel-Crafts. So we add an acyl chloride, it can be bromide, so CH3, COBr, and aluminum chloride. At 50 degrees Celsius, we get phenylethyne. All right. So even if you have benzene plus CH3CH2, COCl, aluminum chloride at 50 degrees Celsius. So here I can still form CO, CH2CH3. That is as far as Friedel-Crafts is concerned. So I'm left with two methods, and that is ozonolysis and the method of hydration of alkynes. Ozonolysis and the hydration of alkynes. So before I go to those two methods, because they are very sharp, still we can get these carbonyl compounds from acyl chlorides. From acyl chlorides, and this method was revised by some guy called Rosemond. So we call it the Rosemond reaction. Rosemond reaction from acyl chlorides. Here, this method is only for preparing aldehydes. For preparing aldehydes. Now, acyl chlorides are reduced to aldehydes by a hydrogen on poisoned palladium. It can be palladium, barium sulfate, and the catalyst is poisoned using sulfur and quinoline. So we have hydrogen. Anyway, let me first consider an acyl chloride, CH3. CH2, COCl. This is an acyl chloride. So acyl chlorides are reduced. So, but we use hydrogen in presence of poisoned palladium, PD, in barium sulfate catalyst. Then you heat. So we said that it is used specifically for preparation of aldehydes. So it will be CH3, CH2, and CHO. Okay. That is it. And how it can be done. So from there, now we can go to those other preparations. Can look at ozonolysis. Now, when we say ozonolysis, here it's a method of obtaining carbonyl compounds, okay? All carbonyl compounds can be formed by bubbling ozone through the solution of an alkene, that is tetrachloromethane, at temperature 20, form an ozonide. Because the ozonide is one that is hydrolyzed using zinc and ethanoic acid. So meaning by having those, then you are safe to go. So ozonolysis, first have an alkene. This is propene. So we want to treat it with whatever that we have mentioned. So we say that we treat it with ozone, first of tetrachloromethane. However, I didn't talk about, I didn't stress the temperature, but put it there because it's a condition for that reaction to occur at less than 20 degrees Celsius. That is the first item to book. The second item, CH3, CH, bond CH3. So when you treat propene with these reagents, we form a mixture of two products. We shall form ethanol and methanol. You form ethanol and methanol from propene. So this first part will give you, this other part will also give you. So that's why we have split it like that. Then the final method of preparation I'm ending with is hydration of alkynes. Hydration of alkynes. This mechanism is always examined, but next time we shall go through them, these mechanisms of the reactions. We've looked at some of them which are possible. Hydration of alkynes. Now, when we say hydration of alkynes, here the carbonyl compounds are formed by reacting alkynes with dilute sulfuric acid in presence of mercury 2 sulfate catalyst at 60 degrees Celsius. So ethyne forms ethanol, while other alkynes form ketones. So in other words, when you treat an alkyne with the dilute sulfuric acid, then mercury sulfate, you wait for it. So we use mercury sulfate as a catalyst, of course, at 60 degrees Celsius. So here we shall form ethanol CH3 CHO. If you have like phenylethyne, that is our compound, phenylethyne. We treat it with all those reagents, dilute sulfuric acid, mercury sulfate catalyst at 60 degrees Celsius, we shall form phenylethanone. So we shall form phenylethanone, COCH3. COCH3. We shall be outlining the mechanisms for these reactions. Also, can have this example: CH3C, triple bond, CCH3. Don't edit. Dilute sulfuric acid, mercury sulfate catalyst at 60 degrees Celsius, and this one will give us it will give us CH3, CO, CH2, CH3. Okay, so after having gotten this, we can now go to ozonolysis. Ozonolysis of alkenes. When we talk of ozonolysis, this is where we form carbonyl compounds by bubbling ozone through a solution of alkene in tetrachloromethane at 20 degrees Celsius. We form an ozonide. Then the ozonide is the one that is hydrolyzed using zinc and ethanoic acid. So how do we use ozonolysis? We shall have CH3, CH, the bond CH2, 1, O3, tetrachloromethane, less than 20 degrees Celsius. Then the second one is, now here we hydrolyze in water. Then zinc and ethanoic acid. Here we shall form ethanol then plus HCHO. Then what if you have CH3, CH, CH, then CH3, it is still the same ozone, tetrachloromethane, then at less than 20 degrees Celsius. The second reagent will be water, zinc, and ethanoic acid. This one will form us, because here we shall have CH3CO, CH3CO. So it is 2 CH3CO. So, as I've told you, all these are essential because we can be using them to derive some schemes, some synthesis. Shall be using all these contents, all these ideas we are getting to carry out some synthesis or some conversions. Now, right now, we've looked at introduction to carbonyl compounds. We've looked at the nomenclature. We've looked at physical properties. And we've looked at methods of preparing it, of preparing the carbonyl compounds, aldehydes and ketones on the laboratory scale. Now, our next video, we shall scrutinize again these conversion methods. We see the ones where we would need to outline a mechanism, we shall do. Then after that, I take you to chemical properties of carbonyl compounds, where we're going to cover nucleophilic addition, condensation reactions, reduction reactions, oxidation, and other reactions as you may think about them. Now, allow me end here for today, wishing you all the best till we meet again. Be blessed.